Several studies have investigated the impact of voltage sags and undervoltage on the lifespan of induction motors, with varying findings. IEEE Standard 1159.2019, titled Recommended Practice for Monitoring Electric Power Quality, includes a section on voltage sags and the potential effects on induction motors, including increased insulation stress, torque loss, and overheating. It notes that the duration and magnitude of sags can significantly impact motor life. A study titled Effects of Voltage Sags on Industrial Induction Motors by M. Collins and H. Hart examined the effects of voltage sags on induction motors in industrial settings. They found that sags of 50% of nominal voltage or less for durations up to 10 seconds had minimal impact on motor life. However, sags of greater magnitude and duration could lead to accelerated degradation, especially in motors with high starting loads. Another study titled Impact of Voltage Sags on Induction Motor Life by N. K. Pand and A. K. Merhanty simulated voltage sags in laboratory conditions and observed their effects on induction motors. They found that sags of 50% of nominal voltage for durations exceeding 10 seconds could significantly reduce motor life, particularly for motors operating at or near their rated load. The CBEMA curve is a widely used industry standard that defines the acceptable voltage tolerance for sensitive electronic equipment. It establishes voltage sag thresholds and durations that are considered safe for most types of electronic devices. However, the CBEMA curve is not specifically tailored to induction motors. While it provides general guidance on acceptable voltage sag levels, it does not account for the unique operating characteristics and load demands of induction motors. There is a lack of comprehensive studies specifically investigating the effects of voltage sags and undervoltage on the lifespan of induction motors. Additional research is needed to determine more precise voltage sag thresholds and durations that can be used to predict the impact on motor life under various operating conditions. This information would enable engineers to select appropriate mitigation measures and design systems that minimize the risk of premature motor failure. To elaborate on voltage sags, consider them as brief reductions in the root mean square, or RMS, voltage. Typically, a sag is defined as a decrease to between 10% and 90% of the nominal voltage level, lasting for a period from 1/2 cycle to 1 minute. These events can stem from various causes, frequently involving faults in the utility grid or large electrical loads starting up, which temporarily draw substantial current. When a voltage sag occurs, it can have several consequences for induction motors. Firstly, the motor's torque production is reduced. The torque of an induction motor is proportional to the square of the applied voltage. Therefore, even a small voltage sag can result in a significant decrease in torque. This can lead to the motor slowing down or even stalling, especially if it is operating near its rated load. Secondly, voltage sags can cause increased current draw. As the voltage drops, the motor attempts to maintain its output power by drawing more current. This increased current can overheat the motor windings, potentially damaging the insulation and shortening the motor's lifespan. Thirdly, the insulation within the motor can experience increased stress due to voltage sags. Repeated voltage dips and surges can weaken the insulation over time, making it more susceptible to failure. In addition to the studies mentioned, it's important to consider the specific characteristics of the motor and the application when evaluating the impact of voltage sags. Factors such as the motor's size, design, load, and operating conditions can all influence its sensitivity to voltage disturbances. For example, a motor with a high starting torque requirement may be more susceptible to stalling during a voltage sag than a motor with a light load. Mitigation techniques can be employed to reduce the impact of voltage sags on induction motors. Some common methods include using uninterruptible power supplies, or UPS, to provide a stable voltage source during sags, installing surge suppressors to protect against voltage transients, and employing adjustable speed drives, or AS, to regulate the motor speed and torque in response to voltage fluctuations. Also, power factor correction can help to reduce the voltage drop caused by large motor starting currents. Regular power quality monitoring can help to identify and address potential voltage sag issues before they cause problems. Monitoring can include measuring voltage levels, sag duration, and frequency of occurrence. This data can be used to assess the risk of motor damage and to implement appropriate mitigation measures. Furthermore, advanced motor protection relays can be programmed to detect voltage sags and take protective actions, such as tripping the motor offline or switching to a backup power source. Regarding the IEEE 1159.2019 standard, it provides detailed guidelines for monitoring electric power quality, including voltage sags, swells, and transients. The standard recommends that power quality monitoring equipment be installed at critical locations within a facility to capture data on voltage disturbances. The data can then be analyzed to identify the sources of the disturbances and to evaluate their impact on sensitive equipment, such as induction motors. The standard also provides recommendations for mitigating voltage sags, including the use of UPS systems, surge suppressors, and other power conditioning equipment. The CBEMA curve, also known as the ITI curve, is a graphical representation of the voltage tolerance of electronic equipment. The curve plots voltage magnitude against duration, defining the region within which equipment is expected to operate without disruption. While the CBEMA curve is widely used as a general guideline for voltage tolerance, it is not specifically designed for induction motors. Induction motors have different characteristics and requirements than electronic equipment, and they may be more or less sensitive to voltage sags depending on their design and application. Therefore, it is important to consider the specific characteristics of the motor when evaluating the impact of voltage sags. In conclusion, the effect of voltage sags on induction motors is a complex issue that depends on a variety of factors, including the magnitude and duration of the sag, the characteristics of the motor, and the operating conditions. While the CBEMA curve provides a general guideline for voltage tolerance, it is not specifically tailored to induction motors. Further research is needed to develop more precise voltage sag thresholds and durations that can be used to predict the impact on motor life. In the meantime, engineers should carefully consider the potential effects of voltage sags when designing and operating systems that use induction motors and implement appropriate mitigation measures to minimize the risk of premature motor failure. Considering the impact of harmonics on induction motors, harmonics are sinusoidal voltages or currents having frequencies that are integer multiples of the fundamental frequency of the power system, typically 50 Hz or 60 Hz. These harmonics can arise from various sources, including nonlinear loads such as variable frequency drives, rectifiers, and arc furnaces. Harmonics can have several adverse effects on induction motors. Firstly, they can cause increased heating. Harmonic currents flowing through the motor windings can result in additional losses due to the skin effect and core losses. This increased heating can degrade the motor insulation and shorten its lifespan. Secondly, harmonics can cause reduced torque. The presence of harmonics in the voltage supply can distort the motor's air gap flux, leading to a reduction in the developed torque. This can affect the motor's ability to start and operate under load. Thirdly, harmonics can cause increased vibration and noise. The interaction between harmonic currents and the motor's magnetic field can generate pulsating torques, which can lead to increased vibration and noise levels. This can be particularly problematic in sensitive applications. To mitigate the effects of harmonics on induction motors, several techniques can be employed. Firstly, harmonic filters can be installed to reduce the levels of harmonic currents and voltages in the power system. These filters typically consist of tuned circuits that are designed to shunt harmonic currents away from sensitive equipment. Secondly, line reactors can be used to limit the harmonic currents drawn by nonlinear loads. Line reactors are inductors that are placed in series with the load to increase the impedance at harmonic frequencies. Thirdly, harmonic mitigating transformers can be used to reduce the propagation of harmonics from one part of the power system to another. These transformers are designed to provide a high impedance to harmonic currents, thereby preventing them from flowing into sensitive equipment. Fourthly, proper grounding practices can help to reduce the levels of harmonic voltages in the power system. A well-designed grounding system can provide a low impedance path for harmonic currents to flow back to their source, thereby minimizing the voltage distortion. Fifthly, using motors specifically designed to withstand harmonic distortion can also help. These motors typically have improved insulation systems and are designed to operate with reduced losses under harmonic conditions. The IEEE 519 standard provides recommendations for harmonic control in electrical power systems. This standard specifies limits for harmonic voltage and current distortion at the point of common coupling between the utility and the customer. The standard also provides guidelines for harmonic measurement and mitigation. Power quality analyzers can be used to measure the levels of harmonics in the power system. These analyzers typically measure the total harmonic distortion, or THD, of the voltage and current waveforms, as well as the individual harmonic components. The data obtained from these analyzers can be used to identify the sources of harmonics and to evaluate the effectiveness of mitigation measures. When selecting an induction motor for a specific application, it is important to consider the potential for harmonic distortion in the power system. If harmonics are likely to be present, a motor with an appropriate design and insulation system should be selected. It is also important to implement appropriate mitigation measures to reduce the levels of harmonics in the power system. Regular monitoring of power quality can help to ensure that harmonics are kept within acceptable limits and that induction motors are operating reliably. In summary, harmonics can have several adverse effects on induction motors, including increased heating, reduced torque, and increased vibration and noise. Mitigation techniques include the use of harmonic filters, line reactors, harmonic mitigating transformers, and proper grounding practices. The IEEE 519 standard provides recommendations for harmonic control in electrical power systems. Power quality analyzers can be used to measure the levels of harmonics in the power system. Careful consideration of harmonics is important when selecting and operating induction motors. To further clarify, let's discuss the impact of voltage imbalances on induction motors. A voltage imbalance occurs when the voltages in the three phases of a three-phase power system are not equal in magnitude or are not separated by 120 electrical degrees. Voltage imbalances can arise from various sources, including unbalanced loads, transformer faults, and open conductors. Voltage imbalances can have several negative effects on induction motors. Firstly, they can cause increased current draw. The motor attempts to compensate for the voltage imbalance by drawing more current in one or more phases. This increased current can overheat the motor windings and shorten its lifespan. Secondly, voltage imbalances can cause reduced torque. The voltage imbalance creates a negative sequence voltage component, which produces a counter-rotating magnetic field in the motor. This counter-rotating field opposes the normal rotating field, reducing the developed torque. Thirdly, voltage imbalances can cause increased vibration and noise. The negative sequence voltage component can also cause pulsating torques, leading to increased vibration and noise levels. Fourthly, voltage imbalances can cause increased losses. The increased current and the presence of the negative sequence voltage component can lead to increased losses in the motor windings and core. The National Electrical Manufacturers Association, or NEMA, standards define the allowable voltage imbalance for induction motors. NEMA standard M-GUN specifies that motors should be capable of operating successfully with a voltage imbalance of up to 1%. However, operation at higher voltage imbalances can significantly reduce motor life. The percentage voltage imbalance can be calculated using the following formula. Percentage imbalance equals 100 times the maximum deviation from the average voltage divided by the average voltage. To mitigate the effects of voltage imbalances on induction motors, several techniques can be employed. Firstly, balancing the load across the three phases can help to reduce the voltage imbalance. This can be achieved by distributing single-phase loads evenly across the phases. Secondly, checking and correcting any wiring problems can also help. Loose connections, corroded terminals, and damaged conductors can all contribute to voltage imbalances. Thirdly, using voltage regulators can help to maintain a balanced voltage supply. Voltage regulators can automatically adjust the voltage in each phase to compensate for imbalances. Fourthly, derting the motor can also help. If a motor is operating in a situation with a known voltage imbalance, it may be necessary to derate the motor to reduce the load and prevent overheating. Fifthly, monitoring the voltage balance can also help. Regular monitoring of the voltage balance can help to identify and address potential problems before they cause damage to the motor. Power quality analyzers can be used to measure the voltage balance in the power system. These analyzers typically measure the voltage in each phase and calculate the percentage voltage imbalance. The data obtained from these analyzers can be used to identify the sources of the imbalance and to evaluate the effectiveness of mitigation measures. When selecting an induction motor for a specific application, it is important to consider the potential for voltage imbalances in the power system. If voltage imbalances are likely to be present, a motor with an appropriate design and insulation system should be selected. It is also important to implement appropriate mitigation measures to reduce the voltage imbalance. Regular monitoring of power quality can help to ensure that voltage imbalances are kept within acceptable limits and that induction motors are operating reliably. In summary, voltage imbalances can have several negative effects on induction motors, including increased current draw, reduced torque, increased vibration and noise, and increased losses. Mitigation techniques include balancing the load, correcting wiring problems, using voltage regulators, and directing the motor. The NEMA standards define the allowable voltage imbalance for induction motors. Power quality analyzers can be used to measure the voltage balance in the power system. Careful consideration of voltage imbalances is important when selecting and operating induction motors. Considering the effect of frequency variations on induction motor life. Induction motors are designed to operate at a specific frequency, typically 50 Hz or 60 Hz, depending on the region. Significant deviations from this frequency can have adverse effects on motor performance and lifespan. Frequency variations can arise from several sources, including generator instability, grid disturbances, and variable frequency drives, or VFDs. When the frequency of the power supply changes, the synchronous speed of the motor, which is the speed at which the rotating magnetic field in the stator rotates, also changes. The synchronous speed is directly proportional to the frequency. If the frequency increases, the synchronous speed increases, and if the frequency decreases, the synchronous speed decreases. The slip of the motor, which is the difference between the synchronous speed and the rotor speed, is also affected by frequency variations. The slip is inversely proportional to the frequency. If the frequency increases, the slip decreases, and if the frequency decreases, the slip increases. Changes in frequency can have several effects on the motor. Firstly, the motor speed will change. As mentioned earlier, the synchronous speed is directly proportional to the frequency. Therefore, a change in frequency will cause a corresponding change in motor speed. Secondly, the motor torque will change. The torque of an induction motor is proportional to the square of the voltage and inversely proportional to the frequency. Therefore, a change in frequency can significantly affect the motor's torque. Thirdly, the motor current will change. The current drawn by the motor is affected by both the voltage and the frequency. An increase in frequency will typically lead to a decrease in current, while a decrease in frequency will typically lead to an increase in current. Fourthly, the motor temperature will change. Frequency variations can affect the motor's cooling efficiency. If the frequency is too high, the motor may overheat due to increased losses. If the frequency is too low, the motor may not be adequately cooled, also leading to overheating. To mitigate the effects of frequency variations on induction motors, several techniques can be employed. Firstly, maintaining a stable frequency supply is crucial. This can be achieved by using stable generators and by implementing grid stabilization measures. Secondly, using variable frequency drives, or VFDs, can allow for precise control of motor speed and torque. VFD can also compensate for frequency variations in the power supply. Thirdly, using motors specifically designed to operate over a wide frequency range can also help. These motors typically have improved cooling systems and are designed to withstand the stresses associated with frequency variations. Fourthly, monitoring the motor's operating parameters such as speed, torque, current, and temperature can help to detect and address potential problems caused by frequency variations. Motor protection relays can be programmed to detect abnormal operating conditions and to take protective actions such as tripping the motor offline. Fifthly, deratting the motor can also help. If a motor is operating in a situation with frequent frequency variations, it may be necessary to derate the motor to reduce the load and prevent overheating. The IEEE standards provide guidelines for the operation of induction motors under varying frequency conditions. These standards specify the allowable frequency variations and the recommended operating practices. When selecting an induction motor for a specific application, it is important to consider the potential for frequency variations in the power supply. If frequency variations are likely to be present, a motor with an appropriate design and insulation system should be selected. It is also important to implement appropriate mitigation measures to minimize the effects of frequency variations. Regular monitoring of motor operating parameters can help to ensure that the motor is operating reliably. In summary, frequency variations can have several adverse effects on induction motors, including changes in speed, torque, current, and temperature. Mitigation techniques include maintaining a stable frequency supply, using variable frequency drives, using motors specifically designed to operate over a wide frequency range, and monitoring motor operating parameters. The IEEE standards provide guidelines for the operation of induction motors under varying frequency conditions. Careful consideration of frequency variations is important when selecting and operating induction motors. The effect of switching transients on induction motor life. Switching transients are short-duration, high-voltage or high-current surges that can occur in electrical power systems when circuits are switched on or off. These transients can be caused by a variety of factors, including the energization of transformers, the switching of capacitors, and the operation of circuit breakers. Switching transients can have several negative effects on induction motors. Firstly, they can cause insulation breakdown. The high voltages associated with switching transients can stress the motor's insulation system, potentially leading to premature failure. Secondly, they can cause winding damage. The high currents associated with switching transients can generate excessive heat in the motor windings, potentially damaging the insulation and conductors. Thirdly, they can cause bearing damage. The rapid changes in voltage and current associated with switching transients can generate mechanical stresses in the motor's bearings, potentially leading to premature wear and failure. Fourthly, they can cause control system malfunction. Switching transients can interfere with the operation of the motor's control system, potentially leading to erratic behavior or shutdown. To mitigate the effects of switching transients on induction motors, several techniques can be employed. Firstly, using surge suppressors can help to protect the motor from high voltage transients. Surge suppressors are devices that are designed to limit the voltage across the motor terminals to a safe level. Secondly, using reactors can help to limit the rate of rise of current during switching events. Reactors are inductors that are placed in series with the motor to slow down the flow of current. Thirdly, using controlled switching devices can help to minimize the magnitude of switching transients. Controlled switching devices are circuit breakers or switches that are designed to operate in a way that minimizes the generation of transients. Fourthly, using proper grounding practices can help to reduce the levels of transient voltages in the power system. A well-designed grounding system can provide a low-impedance path for transient currents to flow back to their source, thereby minimizing the voltage stress in the motor. Fifthly, using motors with improved insulation systems can also help. These motors typically have insulation systems that are designed to withstand the stresses associated with switching transients. The IEEE standards provide guidelines for the protection of induction motors from switching transients. These standards specify the recommended surge protection devices and grounding practices. Power quality analyzers can be used to measure the magnitude and duration of switching transients in a power system. The data obtained from these analyzers can be used to evaluate the effectiveness of mitigation measures and to identify potential problems. When selecting an induction motor for a specific application, it is important to consider the potential for switching transients in the power system. If switching transients are likely to be present, a motor with an appropriate design and insulation system should be selected. It is also important to implement appropriate mitigation measures to minimize the effects of switching transients. Regular monitoring of power quality can help to ensure that switching transients are kept within acceptable limits and that induction motors are operating reliably. In summary, switching transients can have several negative effects on induction motors, including insulation breakdown, winding damage, bearing damage, and control system malfunction. Mitigation techniques include the use of surge suppressors, reactors, controlled switching devices, and proper grounding practices. The IEEE standards provide guidelines for the protection of induction motors from switching transients. Power quality analyzers can be used to measure the magnitude and duration of switching transients in the power system. Careful consideration of switching transients is important when selecting and operating induction motors.